Good morning, everybody. Thank you very much for the invitation. I'm very happy to be here. It's my first time in Bangalore. And as Hamid said, I'm a bit out of context in the sense that I'm not a mathematician. So most of the things that I will mention in this topic will be certainly explained in much more extensively and deep way by the other speaker in the same workshop. So the purpose of my talk is mainly to try to explain, give an overview of what the problem of state estimation has become when applied in the context of environmental prediction, and the type of solution and approximation that the specificity of the problem that we have in geoscience has had as a consequence in the classical approaches. The outline of the talk is the following. So I will first give an overview of data simulation, what we expect from data simulation in the perspective of environmental prediction. A bit more in detail on the data simulation method, which this is exactly the part that I'm pretty sure that the other speaker will explain much more in detail and giving much more mathematical correct framework than where I will be. In the other part, I will try to clarify which are the particular problem that makes the problem of state estimation so difficult when applied to to geophysical context, and trying to also to explain more in detail which have been the solution which has been proposed in the last 2 or 3 decades. And then I will describe a bit more in detail 3 different problems, 3 different novel solutions that try to address the problem that we encounter in this class of application. Maybe I won't have time to go through all the presentation, but still I have time to show the outline. So a typical, let's say, operational definition that we use very often in the environmental context about data simulation is like the entire sequence of operation that's starting from observation on the one hand, possible from an additional statistical or dynamical knowledge about the system, provide an estimate of its state. And this is a very general definition which it aims at encompassing all strategies that we can use to this scope. And I just listed here 3 areas of application where data simulation has been very fruitful in geosciences. The most important one will be certainly numerical weather prediction. And the hydrology is the second point. The third one is the reanalysis. The reanalysis programs are this program that I aim at reproducing the complete Earth system using the same data simulation scheme, the same environmental model, and processing all past observation. The reanalysis programs are very, very important in geoscience because they provide a unique homogeneous picture of the Earth system across almost 1 century. The snapshot here gives an overview, which I want to give an illustration on how data simulation is applied in the context of numerical weather prediction. So we have the observation on the one hand, we have the model on the one hand, we have to show the 2 essential ingredients of this process. And then the data simulation provides the analysis, which can be used for diagnostical purposes and can also represent the initial condition for the next cycle to be launched. Sorry for my. Excuse me?
What did you mean by reanalysis?
Well, reanalysis, it's the word that we use in geoscience to refer to when we process all the existing observation from the very past, essentially from the beginning of the 20th century to now, using the same geophysical model, so the same, eventually the couple model, atmosphere plus ocean, the most recent one, using the most advanced data simulation technique which is applied operationally. This costs enormous effort in terms of computational and manpower, and they are typically done every 15 years by the ACNWF for Europe and the NCEP for US, but there are also parallel programs given by from the German, from the French, from the UK as well, of course. The typical source of information are, again, the observation, which can have a very different origin, can be cyanotic profile, onboard measurement, remote sensing, etc. the background field that it can be the climatological or, as is the case in numerical weather prediction, the outcome of a short-range forecast, and then the evolution dynamics, essentially the model that we have at hand. All these. The synoptic profile, excuse me, right. Synoptic profile are the standard network of measurement used by the WMO, so for the World Meteorological Organization, and they are balloons which are launched at a specific site over the globe and measure pressure and wind in vertical. And they are called synoptic because originally they were scheduled twice a day. And that interval, 12 hours, is considered a typical time of evolution of synoptic disturbances in the free atmosphere, which is a disturbances of the scale between 100 kilometers and 1,000 kilometers. Exactly, yes. The background here is what usually in statistics is referred to as the prior, which can be a climatological field or as it is the case in numerical weather prediction, the outcome. Yes, well, yes. Well, the point, that's another point. So what, the primitive equation model, which represent the evolution of the atmosphere in the free atmosphere, are essentially Navier-Stokes equation. The quasi-geostrophic equation are a very good approximation of that, which used to be used at the beginning of the 20th century as a prognostic model, but its prognostic capability are very reduced in terms of producing real-time forecast. But the model themselves that we use in environmental prediction are much more complex because the Navier-Stokes equation as it is only are good approximation for the free atmosphere. So this is not the case in the proximity of the surface when we have the interaction between ocean and atmosphere or in the stratosphere. So a number of parameterization are then added to this equation. So these sources of information are combined to give the best possible estimated, which is usually referred to as the analysis. And then this figure here is just to provide an idea of how the observational network of the Earth has improved in the last decades. In the left top panel, we have the distribution of the observation in the pre-satellite era. And here we go through until 2006 here, which give an idea on how, thanks to the onboard measurement over the satellite, we now have a much more homogeneous and continuous coverage of observation until the globe. So one of the challenges data simulation has to deal with to face in the last decade in the context of geoscience has been to try to make the best use of all this amount of observation which is now available, thanks to the space agency that launched satellite and blah, 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 blah. So now here I just come a bit more on the formulation, something that you know much better than me, but just to put the problem in the perspective that interests in my talk. The objective is the estimate of a state of an unknown system based on an imperfect model and a limited set of noisy observation. So by simplicity, I can write the model here under discrete form here. So the ham here is taken to represent my model. The vector mu is taken to represent a white noise, which is used to account for the discrepancy between my model ham and the nature evolution, which gives up to the observation here h. And the operator h, which is in the general case assumed to be nonlinear, connect the observable to the system state, and the vector epsilon is used to represent the observational error. In this framework here, both mu and epsilon are assumed to be white in time and uncorrelated between them. An important point is that P, which is the size of the observational vector y, is in any relevant application in geosciences much smaller than n, where n being the size of the system state. So to start with, we are in this situation, in this class of application. So the smoothing, the filter, and the prediction problem are essentially, can be labeled in this way. So the smoothing problem has the problem of estimating the state at all time xk based on all the observation of the same time interval. Similarly, the filtering problem can be posed as the problem of estimating the state xk based on all observation collected up to the previous time. And by extension, the prediction problem has the problem of estimating the system xk at any future time where k is larger than L. Now, sure, of course.
I mean, are you going to have local models which then would have to be tied together, or is this, I mean, X is going to be some global state, or there will be lots of local models?
Well, in this slide, I was not thinking at any distinction of that sort, but I was just meaning that xk is intended to represent my global model, the model whose state I intend to estimate using that observation. But in the practical numerical weather prediction, we have both situations. We either have data simulation for the global model, or we have data simulation for the local model.
But are you going to, is the issue connecting these
Is an issue.
estimates, but also you assume sort of notions of scale and so on?
Well, there is an issue. Historically, until like 5 or 10 years ago, the local model were not using any data simulation because the boundary forcing coming by the global model was assumed to be enough information, and because the local model were only used up to 2 days in the forecast. In the recent time, the frequency of data simulation, which is up to 1 hour or 3 hours in the sequential mode, makes that now even in the local model we are using data simulation algorithms. No, thank you for... I'm sorry. What? I mean that the model, that my model ham that represent all my knowledge, the best possible knowledge about the law governing the evolution flow, are not a nature, which give up the observation. So in that sense, it's imperfect. And the easy thing that we can do is assuming that this discrepancy is modeled through a stochastic white noise process. I'm not saying that this is the best thing to do, but it's...
What you're saying is mu k is unmodeled dynamics.
Yes.
If they're in a system which you don't know, you assume to be a...
Exactly, yeah. Then the problem of prescribing the statistical property of mu is an object of this. Excuse me?
Do we assume this NK and H is known to us? This NK that tells
Yeah?
the evolution. So NK is known to us.
MK is a model equation, yeah. It's the model, yeah.
I mean, it's a parametric form, or this model is completely known to us?
It's completely?
Is it completely known to us?
It's completely known, and this is deterministic, except for that part here. It's completely known.
N also, this dimension N is known to us?
Excuse me?
The dimension N, that is known to us?
Dimension n is taken to represent the state vector dimension. So this is the xk belong to R to n. So in the case of a grid point model, meaning that you have n grid point, or let me say, if you have 3 variables over a grid, so n represent the 3 times the grid point, for instance. And in the case of a geophysical of points, exactly. And just to complete this point, and then I can, to give an example, in a realistic and environmental numerical weather prediction context, n is of the order 10 to 9. Sorry.
Typically in atmosphere, we have that stochasticity in the model dynamics.
No, that's a crucial point. No. I will come back, hopefully, I will come back on this point later. But the equation that we use to make prediction are completely deterministic. Another issue is the fact that we know that this model is not a good representation of the truth, and the way how we model this model error can be and often is done under the stochasticity approach. But the model equations are strictly deterministic. It's the same point that we were discussing before. And so if we want to retrieve this problem under the classical form of a probabilistic approach, we again know that the smoothing problem is now the problem of estimating the conditional probability of xk given yk, and similarly for the filtering and the prediction. This PDF will fully characterize the estimation problem. The things that we need is to have to characterize the pieces of information that enter our estimation using the similar PDF. So in principle, we should know the PDF of the prior or background, the PDF of the model error, and the PDF of observational error. So in principle, should all these objects be at hand, we can solve the problem using the Bayesian. Sorry. K is capital X and capital Y have been defined here. Capital X has been defined like all the collection of all system state up to time K, and yeah. What I was saying. So we know, you know better than me that, you know, in principle we can solve this problem using the Bayesian formula. And so this, under the hypothesis that I aforementioned, this will be the solution for the smoothing problem. The filtering problem is like a sequential problem in which we will have the Kolmogorov equation to integrate forward the PDF, and then we will have the analysis update. The reason why I say all this introduction is just to arrive at, to reach the point in which I have to say that in high-dimensional linear system, this full Bayesian formulation is clearly not affordable. So we have to turn to more practical solution in the realistic application of data simulation in geosciences. So what, from now on, excuse me?
Do you do model reduction?
Not necessarily, but what we do is that we do Gaussian framework. So instead of using a completely Bayesian update, we use a sort of Kalman filter-like approach. That's what I will say now. Linearize, assuming that the aerodynamic is linear. We do not linearize, but we assume that is the evolution dynamics of that sort. That's what I will try to explain now. So now what I would say, that from now on, I will try to explain how certain simplification, certain approximation of the general problem has give up to algorithm with a specific name, and as under this name, they are known in the context of geosciences. The first one is the 4D bar, which maybe you have heard, but in environmental prediction is a very well-known algorithm. The 4D bar is essentially nothing more and nothing less than the solution of the smoothing problem under the hypothesis that the initial condition, observational, and model error are all Gaussian and mutually uncorrelated. So this turns out as to be the problem of minimizing a cost function of this sort here, where we now have moved the problem of characterizing the error associated to each piece of information under the form of fully PDF. We only need to know the mean and the covariance, because we are assuming that these objects are all Gaussians. And this is what is used, the 4D var is what is used in practice in most of the climate service worldwide, such as the UK Met Office, the ACNWF, and I think the Japanese as well. And the French, of course. Sorry.
So, first of all, this is not really solving the smoothing problem, right? Because you're only getting the maximum of the posterior distribution, but you're not getting any error bars.
Well, when you minimize that,
this is the map estimate, right?
Well,
Assume a posteriori estimate.
you are assuming the point is that if you minimize that with respect to the trajectory along within the interior time interval.
Linear case.
Because this is the space-time density of the nonlinear system, right?
Well, this is
only the initial condition goes.
No. Well, if I minimize it here, I'm assuming that this cost function is function of the interior trajectory within the interval. So the control variable with respect to which I will do my minimization will be the interior trajectory. If it is lumped over n time step.
The maximum likelihood trajectory. This is not solving this is not finding the initial distribution of the trajectory. This is just finding the maximum likelihood.
Absolutely. Yes. Yes.
So
yes.
it's not telling you anything about the distribution.
Yes, so you are right. So I'm contradicting what I say in the previous slide. I'm not strictly solving the smoothing problem. I'm finding the best possible estimate of this system, which give the best misfit between the model equation and
This is map, posterior map, exactly. But if they're doing posterior map, how do they get, because if I listen to the forecast, I get it's a 30% chance of rain. Where does that come from? If they're not, because they're not finding the uncertainty from this model, right? So
no. Well, that's another point. So you are, well, okay, but we are jumping to another point. In this way, we are not solving the problem of predicting the uncertainty, which is what you are saying now.
no,
This,
that's the same point, because the smoothing problem would be.
yes, but we are not able to explicitly have the PDF. We only have the estimate here. So that's the problem of this data simulation here is giving you the state, the best possible state of the system. If you want to have an information about the uncertainty associated to that prediction, that's an important topic that will go later on this point, but this has not been solved for the problem of the huge system we have at hand in the framework of the variational scheme in the environmental science. What we do is using an ensemble-based scheme, and we use the ensemble to estimate the uncertainty associated to that specific prediction. So the answer to your question from where the 30% of rain come from is essentially the distribution of 15 up to 100 ensemble members which run the same deterministic model with small perturbation in initial condition. That gives you what you see in the TV, like the 30% of raining in Oklahoma is that one.
So if I understand correctly, so you first solve this problem, this variational problem, you first find the point.
No, if I solve this problem, I don't do what I said before. There are competitive schools in the environmental science. On the one hand, there is the center that make variational schemes, and they do not provide any associated information about the predicting uncertainty, what is called EPS, Ensemble Prediction System. They are not doing so, and for this reason, in the last decade, this approach has lost attraction. And then there is a competitive school which goes beyond the so-called ensemble Kalman filtering, which is something that you will certainly know, but that has referred in this way in that community. And the advantage of ensemble Kalman filter, among other things that I will try to say, is that they provide also not only the best possible estimate, but also the associated uncertainty to that, which is used from a user point of view to give, okay, it will be raining in Oklahoma, but the chance of raining is that one. Yes.
Sorry.
No.
So you need a whole trajectory of observations to solve this variational problem.
Yes.
So how does that work in practice? Is there a window?
Does not work. So this approach, this is what I will explain later, but we are jumping.
Okay.
This is what we would like to have in principle, but we don't do that. What we do in practice is what is called a strong constraint for DVAR. So we assume that our model is perfect. So instead of minimizing with respect to the entire trajectory, we only minimize with respect to the state at the beginning of the simulation interval. So this reduces enormously the computational cost of the problem. And we minimize using a descent approach, using the gradient essentially, with respect to the initial condition alone. So the problem of the then we repeat again and again and again. So
this is not recursive, right? So how long of a window of
and the window in which we use this approach is not longer than 40 hours in realistic application. But in I didn't know this. But this aspect is very important because in the languages that we use, the fact that we minimize, assuming that the model is perfect, so this part is cancelled, and we only minimize with respect to the initial condition, is usually referred to as strong constraint because we append our model as a strong constraint. Yes, the model is covered, but only recently we are moving to application in which we are adding this term in realistic application. I'm saying not in toy models, and we are adding this. And we refer to as the weak constraint formulation. All these things are topics of my next slides, but we are jumping. It's much.
It's essentially an inverse problem.
It's an inverse problem, yeah. Yeah. Excuse me, there was a question. Sorry, I'm sorry. With respect. Well, in principle, I should minimize with respect to the entire trajectory with respect to the interval in which my observations are collected. But in practice, in most of the application, because we cannot do that for the huge size of the system we have at hand, we only minimize with respect to the initial condition. and we assume that the model is perfect. So by knowing the initial condition and the initial time, give us univocally all the state in the interval.
I'm just trying to understand.
Sorry, let me. XB here is the first guess. The first guess. And, excuse me? Of the initial state, yes. Because we assume that we only have a guess for the initial condition. This is typically, can be, as I said before, can be a climatological field, giving the distribution of temperature, pressure, and all prognostic variable based on the mean of a sufficiently long time, or can be the outcome of a short-range numerical weather forecast. Oh, sorry.
About Raman's question about how do you, it's not, it is in a sense sequential, in the following sense. You do explanation of this function over several time periods.
So let's say 40 hours ago we did this thing, we got the forecast until now. Now we
Yeah, and that you can put
Then
in
you
as
redo it for the next one.
So that's XB. So now we get a point forecast from this.
That-
We use
that's
that
the
XB.
XB. For the
And
next
how do
time
you
we-
choose this matrix big B?
Well, that's another big problem. Most of your questions are the topic of my next slides. Estimating B is the big issue. Okay.
All right.
Sorry. Anyway,
So why don't we go on? Yeah.
estimating B is the big issue in environmental science. So the entire history of the data simulation in environmental prediction until the time when Ensemble-Kalman theory came on was how to estimate this one. Because this guy here is big. Because X is 10 to 9, so this is a 10 to 9 times 10 to 9 matrix. And it's intractable. So we need to parameterize that, we need to do something. And one of the big problems, and one of the nice things is that the model is chaotic, which should be considered a problem, but sometimes it's not a problem because it makes that we can use the chaoticity in a way to prescribe a way to confine this matrix B in some intelligent way. Now I'm jumping through, but this is, maybe you can say more about this, but, and what?
Boys are not known, right?
Excuse me? Excuse me?
And the previous slide, the new Y's are not known, right? The new Y's in the first one, they are the error. New Y's, the first one.
The mu i's,
But the new Y's,
the mu I is actually
I don't understand what mu
xi
is.
minus
Mu I,
m
okay.
times xi minus m of xi minus.
Yeah. Yes.
So mu I
This
are
one.
are functions of xi.
This one.
Of xi.
Just perhaps something to clarify that in some sense there is a strong connection between this minimization and the smoothing problem, because the smoothing problem is a problem of estimating the entire trajectory of the signal from time 0 up to the current time based on all the observations. And this one does the same thing in some sense, except that from the Bayesian perspective, you look at the conditional distribution of the trajectory here, we just get one path via this.
This is exactly the point. It was what was outlined from him as well, yeah.
It is an attempt, a practical attempt to solve the smoothing problem.
Well, now in these slides, the idea of this slide was to try to collect most of the comment about how variational 4D var is done. Most of these things have been already partly discussed so far. One is the fact that the sequence of trajectory which minimizes J is a maximum likelihood estimator of the PDF. This provides the best possible fit given the initial guess and perfect model. The strong constraint 4D var makes a sum, which is the one which has been used in practice up to nowadays, makes the assumption that the perfect model and the latter is appended as a strong constraint when we do the minimization. The minimization of a change can be done by solving the associated Euler-Lagrange equation. There is also a method which is in geoscience known as the method of representative, which has been done by people by Bennett essentially in Oregon, which has been very useful to apply the 4D var in the context of ocean model. And in the case of linear equation, it used to be very, very, very powerful. And now, the problem is that the matrix B, let alone the moment let alone for the moment how we have prescribed this matrix B. But when we make this matrix B, which is the matrix that you mentioned before here, I should have used the same color, is implicitly evolved within the simulation interval. But at the end of the minimization, we do not have this matrix, the new matrix at disposal. And this is an issue. Then I will come back on this point.
Theoretically, is B a sparse matrix?
Excuse me?
Is that a sparse matrix?
I don't know.
Or is it much more local? Okay.
Should, yeah, I guess
Well-
you should have a local structure if your model
Well,
local interactions, but I don't know if it's proved theoretically or not.
well,
Expectation.
well, the property of this matrix B, of course, reflect the physical property of the model. And as such, of course, the terms close to diagonal would be much larger than far from diagonal. This is for sure. But there is also an additional point. Well, I don't know really in practice what they became, but certainly true that for a chaotic system, the rank of the matrix B tend to be as large as the number of unstable or the stable direction of the system, which are in general much lower than the size of the model at hand. No, thank you. And another practical algorithm, which is can be intended to be as an approximation of the 4D var, usually referred to the 3D var in the environmental context. In 3D var, we're essentially assuming that all the observations happen at the same time, and we make the minimization with respect to that time. So essentially, the 3D var is like a classical optimal interpolation approach. Now, here I mentioned Met Office and ACWF, but also the Met of France use 4D var as an operational system, because the 4D var that we know now in the community has essentially been initially invented from people in France. Well, at the opposite of this variational approach, there is a sequential approach, and certainly you know that under the same hypothesis of Gaussianity and mutual uncorrelation of error, the filtering problem reduces essentially to the estimation of the mean and covariance. Here we have the very well-known analysis update equation giving the update of the state estimate, the associated error covariance, and the matrix K, which is the Kalman gain equation. And the Kalman filter, you know very well, is the filter which is applied for linear models and for linear connection between the model and the observable. So certainly, the class of application we are discussing now are not ideal for this kind of approach. But it is also the second problem, which is the problem of the size, again, the size of the system that we use in realistic numerical weather prediction. But anyway, the extended Kalman filter, so the first order approximation of the Kalman filter in which we use a linearization to propagate the error from one observation time to the next one, has been also explored in geosciences at the beginning of the 90s. And it is almost operational right now for the assimilation of the soil analysis at the ACNWF. Which has been a very recent thing, but it's true that the problem is much more easy for the soil because first, the size of the system is much smaller. Second, the models are not chaotic, and most of the time, the extending Kalman filter for this application that I mentioned here is used under what is called as a state augmentation formulation, in which we essentially use the AKF to estimate the parameter. I will come back also to this point.
What is soil analysis?
Soil analysis means the data simulation applied to the soil model. A soil model essentially is a model which describes temperature and water content in the layer of the soil, which can be, if it is a full hydrological model, the detail and the number of layers can be even 100. But typical soil analysis referred to be these 3 or 4 layer model which are coupled to atmosphere and ocean model and give the feedback between the water content which is contained in the soil and can evaporate and the amount of rain that is in the atmosphere and go down. So typically a soil model is a system of OD with a prognostic equation where prognosis variable are temperature and water content. And the problem of making data simulation for this model is the problem of estimating the state of this model based on indirect observation. Typically, these observations are called screen-level variable observation and represent temperature and pressure at the lowest atmospheric model level, which is typically at 2 meters.
This is not a model that's used for weather forecasting?
No,
Oh, okay.
no.
This is a different...
No. Now, we are jumping, but anyway, it's much better in that way. But now, originally, the numerical weather forecast was based on atmospheric model alone. As in the recent year, we have learned a lot from the climatic context. We have learned a lot about the coupling models. And also, the computational power at our disposal has increased enormously. So the new frontier, and something that is also on the way on, is using fully coupled model, including also soil model, to make also numerical weather forecast. But certainly, in the time scale of 1 week, which is intended to be the numerical weather forecast, the memory of the ocean and the memory of the soil can be neglected with not too much worry. Absolutely, yeah. There has been, but the soil is almost stable. So the soil model are not chaotic. So most of the problems connected with divergence are reduced. And well, certainly the most successful way in which the sequential scheme have been applied in the context of environmental prediction is under the family of the ensemble-based scheme. In the ensemble-based scheme, we use an ensemble of trajectory to approximate the forecast analysis error covariance using, so in this way. So this is just an illustration in which we have the ensemble, which we use to define the analysis error covariance. This ensemble is then, in each member of this ensemble is integrated using the nonlinear model. This nonlinear evolution gives us a new forecast, a covariance based on the ensemble, and the cycle can be repeated. Well, in this thing, I was thinking now very in generally, but I was mainly focusing now on an ensemble of initial condition. But there is no doubt about it that you can also make an ensemble in the parameter and whatever. So there is not a problem. But originally, the problem was that the first application was in the initial condition. And the point was that surprisingly, let's say surprisingly, but the good point was that we can have very good performance even in a model whose system state is 10 to 7, 10 to 8, 10 to 9, using as low as 100 ensemble member alone. So this was the key of the point that opened the door in the last decades to all this class of algorithms. Was distinction I will try to explain in the next slide. But the key point is that given that M has to be much smaller than N for this type of approach to be suitable in this class of application, the good point is that it works. And the point... Yeah.
Initial condition as a mixture of initial ensemble as a mixture of initial conditions and parameters?
It is what people do in practice. It's absolutely, yes, yeah. In this talk, I was wanted to give just an overview, not specific detail. But the state of the art, and even the state of the art of yesterday, is that people do joint state and parameter estimation using ensemble Kalman filter formulation in which you perturb simultaneously state and parameter. Then there are a lot of problems connected to that, and I'm sure that most of the other speakers will explain this problem in more theoretical framework. But the key point is that we do not have a model for the parameter evolution, while we have a model for the system state. So then there is another practical problem which is very well known, is and in the realistic application is extremely important, is the fact that we need to maintain alive the correlation between the observable and the parameter. Otherwise, we will not be able to update the parameter using the observation. And this is another key problem in any application of that sort when we want to make joint parameter state estimation. Anyway, in this slide here, I only wanted to highlight the general reasons that have made this type of approach so attractive for the environmental prediction. I highlight here the fact that the way how we modify the forecast analysis covariance, the forecast error covariance based on the ensemble into the analysis error covariance based on the ensemble is a key point that make a distinction between what are referred to as stochastic or deterministic approach. This is like a subfamilies of this general family of ensemble-based schemes, and the essential difference is that in the stochastic approach, to which the ensemble Kalman filter belong, each ensemble trajectory assimilates a different realization of the observation vector and undergoes an independent analysis update. In the deterministic, also referred to as square root approach, the transformation from the forecast error covariance into the analysis error covariance is made through a linear transformation T. This transformation T is then prescribed a priori based on some assumption. Again, without going into the detail of this distinction, from the point of view of the application that I will mention here, the differences are enormously. And again, I hope to be able to give some results later. Well, let's say, anyway, let's jump at least to some results. So this is an example in which we can compare, you can see what is the difference and the advantage of variational versus the ensemble-based scheme in a realistic case. The model is a quasi-geostrophic model of approximately 10 to 4 degrees of freedom and represent the semiotic evolution in the free atmosphere in the extratropics. We are comparing essentially 3 algorithms. One is an ensemble-based scheme referred to as local ensemble transfer Kalman filter. It is not important with the specificity of this algorithm. Just for your information, this is the algorithm which is operationally used now at NCEP in US to make forecasts for users. On the other side, we also have the 4D-VAR, so the variational scheme, having the 2 different windows for the observation, 12 hours or 24 hours. The third algorithm is 3D-VAR. In this panel here, in colors, we have the background error expressed in pressure at the mid-level of this model. This model has 5 levels. So the colors here and here give the background error at specific time. The contour, so the background error is the actual background error. So it's the error that we want to correct using the observation. So if our assimilation works properly, means that the analysis increment, which is the correction that we give to the forecast, should reproduce this pattern. So when the background error is large, we want that our correction is large. This is the situation in which our data simulation is working properly. So here I compare the 3 analysis increment of the 3 algorithms, 3D-VAR, local ensemble transform Kalman filter, 4D-VAR with 12 hours. And if you compare this column here, you can clearly see that while the 3D-VAR correction are mostly isotropic, and this isotropy does not reflect the complicated structure of the background error in color, and from where this isotropy comes from. This isotropy comes from the hypothesis that we have done in setting the matrix B that you mentioned before. So in the 3D-VAR, the matrix B is static and is prescribed a priori using some physical information about the system. In particular, the B matrix that I've been using in the application that I show you there is using what is called the NMC method, standing for numerical. Yes, thank you. And was the standard approach used up to was an approach used until the beginning of 19 and comes from Parrish and Derber in US. Essentially, you estimate the matrix B by taking the difference between 24-hour forecast minus a 12-hour forecast, and then you use this metric as static. So the point that I think that I do not have time to say more, but I want to highlight this aspect here, is that if you see the correction of the 3D-VAR does not change in time. So despite of the fact that the background error in color can have a very complicated structure and be a consequence of also the chaotic growth and evolution of the underlying dynamics, the 3D VAR is not correct in a way which is coherent with that. If you compare that with the local ensemble transfer Kalman filter, which on the other hand make a correction based on the ensemble, so it's time dependent. So the way how the forecast error covariance matrix is estimated is time dependent by construction. It has been able to reproduce much better. So it's 0 where there is no error, and it's large where the error is present. And the 4D VAR, in 12 hours, it does quite well as well. And these are the error for the forecast error as a function of time for the 4 algorithm. You see that you need 4D VAR with a 24-hour window, which costs a lot in terms of computation, to do better than the local ensemble transfer Kalman filter in blue, which is in this application is only using 50 members. It as in 3D VAR. Yes. Well, but it's static, but it's implicitly evolving. That's why when you make the correction, when you show the analysis increment here, they also have a structure, because we use this B here. This is fixed, but then when you make the iteration, it's like that you are implicitly evolving that, but you don't have this matrix B at disposal, so you cannot use for the next cycle the B which is taking into account how good your estimators became. I think that I don't have much time, no? It's more? Ah. So all this was as a premises to say that when we deal with geophysical system, I wanted to list here the main point, the main problem that we have. One of the problems is that the ocean and the atmosphere are example of nonlinear chaotic systems. So we need to have what is referred to as a flow-dependent description of the estimation error, the covariance that I just mentioned. And this has motivated the growth of a number of family of algorithms such as ensemble Kalman filter, maximum likelihood ensemble filter, assimilation and stable subspace. There are a lot of sources of nonlinearities which represent a challenge for our linear Gaussian approaches. The nonlinearity clearly comes from the model, from the observation operator, from the first guess, etc. The other problem is that the models are not perfect, and this error can be originated from a very different sources: incorrect parameterization of the physical process, numerical deserialization, the lack of resolved scale, etc. And the last but not least is the problem of dimension. So any solution we try to find have to be conceived for a model having the size that I just mentioned before. Given this problem, I then identified 3 different issues, so 3 different lines of investigation in which the novel solution should be provided. I won't have time to go through the 3 of them, so I will just talk about the method to account for control of chaos in data simulation for environmental prediction. This, well, I will jump this part, which is the part in which I wanted to explain which have been the solutions that have been proposed in practice in the framework of the variational and ensemble scheme. And well, maybe I should mention these results here. This is another result in which you can see how the fact that the system is chaotic in a way can represent an advantage, because for certain type of ensemble-based scheme, in particular the square root deterministic filter, such as the extended ensemble transfer Kalman filter here and the maximum likelihood ensemble filter here, what is observed is that the convergence of the filter is reached as soon as the number of members that you use to construct your ensemble exceed some measure of stability of the system. In particular, we found that it was extremely connected to the Kaplan-York dimension of the model. So as soon as we pass the size, or we pass the Kaplan-York dimension, our model, our filter reached convergence. The Kaplan-York dimension. The Kaplan-York dimension is an approximation that gives you an estimation of the dimension of the attractor for a chaotic dissipative system, and is related to the spectrum of the Lyapunov exponent. Yes. It's called Kaplan-York because...
It's a number of unstable modes.
No, it's not the number of unstable modes. It's larger than some unstable mode, and give you the fractal dimension of the attractor for the class of systems which are chaotic but also are dissipative otherwise, and which is the class of model that we use in any realistic application. The point of this result is given in the interpretation here that maybe is obvious for a mathematician, but from the perspective of the application was not so obvious, is the fact that stochastic filter like the ensemble-Kalman filter on the one hand and deterministic filter like the MLAF on the AKF on the other behave in a different completely way when applied to that class of algorithm. So the problem of the computational limitation that we have that sets a limit in the size of the ensemble is completely different. In the ensemble-Kalman filter, we need to increase the ensemble to get better and better result. Using the deterministic filter, we converge to the same result as soon as the size of the ensemble exceeds the Kaplan-York dimension. So it's connected to the stability property of the system. Excuse me?
One has to exploit the qualitative properties of the nonlinear dynamical system in the filter itself.
And that's what we are doing. Yeah. So why don't exploit that?
Exactly.
Yes.
How are you exploiting that?
Well, this result was not exploiting that property at all. It was just looking for a connection between a property, intrinsic property of the model, and the filter. And that's what one point. On this algorithm, like the simulation and stable subspace, but this is not the only one.
It's related.
It's related, yeah.
See, the Kalman filter problem for an unstable system is an easier problem than for a stable system. Because an unstable system injects more energy.
Yes. Well, it's a new way of thinking of the problem, but for me, at least. What I can tell you is that in that type of context where we have such a low observation to constrain the evolution of such a big system, the chaoticity is a problem in the sense that if we do not have enough observation good enough to counteract the error growth, the error easily jump to very high level and
The sensor function should be over the spaces of positive decimal small. If your sensor function doesn't have any information from the positive group, your filter doesn't use it.
yes. And that's the key.
That's sort of the key to what he's trying to say.
No.
So when you have the sensor function is the one you have to choose how to collect data.
And the point of, I completely agree, and the point of, the problem that we have in practice is that we have systems which are chaotic, so a small error in the initial condition will eventually grow very fast, and we do not have enough observation to counteract this growth. So I understand that from the point of view of maintaining the covariances alive, the fact that the system is chaotic can be a good feature, but we are in the opposite situation. We are in the situation in which we have a reduced amount of observation, and we want to use this observation in the most intelligent way. And the most intelligent way is confining the correction within the unstable subspace of the system, which is for the class of chaotic dissipative system much lower. And this is, for instance, what we are trying to do here. And this is, I'm pretty sure that you will also mention other type of algorithm installed.
What I'm saying is that the Kalman filter problem
Yes.
for an unstable system is an easier problem than for a stable system.
Because it is not sensitive to initial conditions. See, if unstable or stable is linear. This is a nonlinear problem. It's not chaotic, which means the initial condition, you can have a small error in the initial condition. And in finite time, you will have lot. And that's what, if it's a chaotic system, it becomes a bit more of a So it is a bit different.
For instance, in this way here, this is the standard. Okay. This is the standard update. We are confining the correction in the columns of the matrix E which is a rectangular matrix, and the column represents the unstable subspace of the system. Let alone now thinking about how we estimate that, which is, I do not have time to explain that, but just to conclude with some application. This is again a quasi-geostrophic model. Here, a classical problem that we have in geoscience, which is a problem of targeting observations. Again, given that we have a few observations, can we find an intelligent way to select the location where this observation will give the best profit for the business of the prediction? So this is the type of problem.
So is it unstable subspace for which state?
Well, for the solution. For the forecasting, yeah. For the solution of the forecast plus observation. So my system is, my model is integrated, I make the observation.
The ultimate direction in these models are state dependent.
Yes, so that's why I didn't want to explain. So the way how I estimate this unstable subspace is time dependent, and is based on an approach which is referred to as breeding on the data simulation system, which is an approximation of the standard technique from Benettini and Galgani to estimate the Lyapunov exponent. We make a sort of the breeding mode, which has been used by Genia Kalnay and Total and SEP, which is essentially use a nonlinear model, and we keep this evolution, we renormalize periodically this. And the difference between the standard breeding and what we use here, which is referred to as breeding on the data simulation system, is that in the standard breeding, this procedure is applied to the solution of the forecasting model alone. Here we use that to the solution of the forecasting model updated by the observation at the observational time. This type of application here is, again, the problem, as I say, it's a problem of targeting observation. We have a solution, we have a problem like that. So we have a land which covers 1/3 of the domain where the observations are densely, and then we have the ocean completely void of observation. And we are comparing 5 types of experiments. In the first experiment, we only have land observation which are estimated, which are assimilated using 3D VAR, using a B which is estimated using the NMC method. And this gives the error here, or RMS error is about 0.4. The second experiment is an experiment in which I locate a fixed observation in the ocean. This fixed observation is again a vertical profile, as the same that I mentioned before, but this position is fixed and is in the point where statistically the ocean error is larger, and give the error here with of 0.3. The third experiment is an experiment in which my vertical profile in the ocean is randomly moved. So every 12 hours when I make the simulation, I locate my vertical profile in different point in the ocean. And so I do something better than just a fixed observation, and the error is further reduced. Then I apply the 3D VAR BDAS method. So in this other experiment here, I'm looking at this BDAS mode, so this perturbation, and I'm looking at it, I'm inquiring where it attains its maximum value, and then I say, okay, I will place my observation in the point in which my unstable mode attains its maximum value. I place a vertical profile there, and I assimilate this vertical profile plus all the land vertical profile using a 3D VAR. And this is the error that I have here. So you see the stronger reduction that we are having by using this dynamical consistent wave of positioning the observation. The final reduction is obtained when not only this observation is located using DAS, but we also use this unstable mode structure to make the correction. So we make the confinement of the analysis error correction within a stable subspace.
Yeah, the way you estimate the RMS error, just trying to understand.
RMS error?
RMS error.
Yeah.
Are you using the same data for the
Absolutely. The RMS error, the RMS error is the true RMS error, because all this experiment is done in the context of a twin experiment. So I can calculate the actual error. And the RMS error there is made in the norm of...
So when you minimize using this model, isn't it the model itself is minimized by using this original data itself?
No. No. This is the actual error. It's not respect to the data. Because even the data here are synthetic data. So this is what is referred to as observation system simulation experiment in which I have my model and the replication of my model, and I use one solution of my model, and I sample this solution to create synthetic observation, and I add noise with some property that I can prescribe, and then I make a fake data simulation cycle using the solution of the other model and assimilating these observations. So I can estimate the real error. The problem maybe is rather the problem of selecting the right norm for the RMS error, but that's another issue. But what I wanted to highlight here was the point that if we can use the information about the chaoticity, we can do something better in both ways, either by just inquiring where the unstable mode is larger and say the error has grown fast there in that specific point in the spatial, and I can place my observation there. But even I can do something even better. If I look at the spatial structure of this mode, I can look at the spatial property of this chaoticity, and so I can use this to correct where I'm expecting that the error will grow fast. That's the point of this slide. And it's also the point of this one here in which we wanted to design the DA algorithm in order to stabilize the system. So I think that we have been discussing this result when we were in Rome, but here we were asking if can I design my data simulation algorithm with a specific purpose of reducing the instability. And as a byproduct, I also have a strong reduction in the associated estimation error, which is the scope of the goal. I think that I should stop here because, sorry.
I mean, is it clear if I heard you correctly, you said you wanted the structure of the data assimilation algorithm to reduce the instability?
Yes, this here was like a change of paradigm. We can say, can I design my data simulation algorithm, in particular the structure of the matrix B, in order to reduce the instability? So that's what the point. So it's like, given that the matrix B is the key of the problem, the matrix B give the form on how the observational information are spread out in the entire model domain. Excuse? R14. I've never considered there was a number there. What is the typical size of what?
We got the result. So what is the size of ensemble size?
Well, in this application, the ensemble size is 50. And this is also quite typical in practical application. Most of the number that I gave in this talk have been taught in terms of the global weather forecast problem. And in that case, so far, nowadays, we can afford, and what people is affording is a size of 100, for a model having a size of 10 to 9. But the application of ensemble-based scheme, excuse me?
How many unstable models?
Well, do you know how to calculate that for a 10 to 9 model? That's a good point, but well, they are. Well, yeah, that's what people say. 20 to 20%, yeah. 20%. Yeah. But then there is another problem there. Most of this model have, suppose a realistic model now has a scale which is also non-hydroscalar, is a scale of 10 kilometers. So if you take even the first 10 Lyapunov modes of such a sort of model, that mode maybe are not so relevant for the business of the prediction that we want to do. Because these errors, which are the errors that grow faster, will saturate at a level which is not very important for the type of error that we can observe for our network. So there is also that type of problem that we have to select the scale that we are interested with. I don't know if I explain myself very well, but
96 is one of the larger models.
yeah, but the problem, the model that we have that we use in practice, the first Lyapunov exponent will be referring to process which are not really relevant, such eventually even in the Brownian motion of the molecule of the hairs. So this grow fast error will saturate at the sites which you cannot even observe with your observational network. So when you really want to design a technique to select the instability and connect the sites to this stability that you want, you should not really think in terms of how many Lyapunov positive Lyapunov exponents you have. Rather, you should think about how fast, how many unstable modes you have in the scale that you can resolve in your model. It's
The scale doesn't enter your picture.
excuse me?
I mean, the idea of scale, as I understand it, in all this work, doesn't enter explicitly.
No, because this was the very last part of my. This was the very last part of my. The very last part of my talk was the data simulation of coupled dynamics and scales. That was, no. Oh, sorry.
But my guess would be, you have to understand, it should be sparse. And one should be able to exploit it sparse. Or it should be
What?
sort of a banded matrix or something.
I think you're doing that. You say local ensemble. Aren't you doing that?
Well, no. Local there is local geographically, and is sparse in that sense. But the problem of scale that I had in mind, and it's considered to be the urgent problem in data simulation, at least in the context where I work, is not in that sense. Is in the sense that there are two ways. One way is the fact that we now want to do coupled data simulation for a system like atmosphere and ocean. There it's clear the separation of scale. You have the ocean with scale instabilities of the order of 10 days, so the perturbations that are relevant from the perspective of the prediction of the ocean are 10 days, while in the atmosphere is 6 or 12 hours. And I'm not thinking about the Lyapunov mode, etc., because, well, in that problem, if you want to make an ensemble data simulation scheme and using the ensemble to create the matrix B, you have a concrete problem of selecting the instability in such a way that the atmosphere does not converge to a level in which it's like noise before the ocean has grown. In that sense, the scale is a problem. But the local that you mentioned there it's another thing that I had not mentioned time to refer is does not really think about the scale in terms of temporal scale. It's scale in terms of the spatial scale. So you make a local ensemble Kalman filter because you are assuming that locally the structure is correlated in that area and is not very well correlated far from there.
I mean, this is completely up the top. I mean, can one conceive of doing something like normalization theory?
I don't know how to reply to you.
You would look at the problem at different levels of scale, then you move from
SPDEs are done now using visualization routine. So if you have a for the filter with small different scales, you could do that possible.
and then maybe course
Just have
line.
yeah, homogenization is done with scales. Is that possible? Yeah, Martin Ira has been working on this. The much more filtering for SPDEs, and this can be extended to these problems. What would be a good toy model if we wanted to understand the data simulation? Now, just a simple.
Well, there are a lot.
The models you're talking about are extremely complicated.
Yeah.
They have lots of different coupled layers.
But most of the models that we're working with, before moving to the Climate Institute where I work now, are considered to be toy model. There are different toy models. One is the Lorentz 63 model, of course, it's very simple. There is also a version, yes, but there is also a version which is just a replication of the Lorentz model. You can coupling, changing the time scales, and you have like a sort of climate model coupling with the atmosphere and the ocean using the same one. Then there is a Lorentz 96 that he mentioned, which is a very good example of a spatial extended chaotic system. And again, you have the original version, which has been presented by Lorentz in 96, in which you have two scales, and you have like I think most of the results that I have were in that model, but I'm pretty sure that he will also show this model again, so he will explain. It's a very simple model. The quasi-geostrophic model that I mentioned, despite of being 10 to 4, is a toy model as well, because it can run on your laptop, and it's extremely complicated from the perspective of designing a data simulation system, but it's still far away from the type of complexity that you can have in practice. And another model that is I'm using now is a model which has been is a couple model, because I'm working on the couple toy models. It's a model which has been published by Van Nitsem in Kalman Dynamics in 2013. And again, it's a simple model having an atmosphere in the ocean, and simple. So I'm talking about 13 variables. And what more? There are plenty of them. Yeah. But there's also a lot of models you can find on the web. I can give you also the web.
That you Stokes itself is not the toy model for this type of thing, because it doesn't have the coupling aspect.
Does not have the what?
Coupling, the two.
Well, but I mean, the problem of coupling is a problem that people, at least from the point of view of the MAO community, people is interested in the recent here, was not the coupling the essential core of the problem. Historically, people want to have a toy model that at least has a doubling time for the perturbation to grow, that in a way or in another resembles the one that we observe in the atmosphere. So the main aspect that you pretend that your toy model will represent is that one, because the big business was the control of growing error. Now the business is no longer that one. The business now is designing data simulation algorithms for couple dynamics. So when you want to make a toy model, or want to select your toy model, you are no longer more stressed about the doubling time, but you are more stressed about the separation of scale. You are more stressed about which type of coupling they can have. Is mechanical, is thermical. So it depends about what you want to do with your toy model.
My question here is, when you're assimilating the data, is it below the doubling time, or is it discrete?
Well, all the application that I mentioned here, I did it in a way which is comparable. So it's the doubling time of the atmosphere is today. All the time I select the interval is been as is done in numerical weather prediction. So if the numerical weather prediction application, the ratio is that, I did the same. To be honest, I don't remember now the. Thank you. Oh.